We're moving on to our second section on semantic processing. And I'd like to introduce and turn it over to our chairs, Alexander Kuzmanovich from Northwestern University and Amar Subramanya. We sort of practiced that a moment ago from here at Google. So, gentlemen, please.
Thanks, Andy. That was pretty good. So, everyone, my name is Amar Subramanya. I'm a research scientist here at Google. So first off, welcome to Google, and welcome to this session on semantic processing. So we have a bunch of really nice talks lined up, so I don't want to take too much time away from the speakers. So what I'm going to do now is just give a very brief overview of what you're going to hear today and tomorrow. So semantic processing has contributed and continues to contribute to a lot of the technologies that we use every day. So be it having the ability to search through a large document corpus. So if you wanted to look for a research paper, or if there is an article in Spanish that you want to translate to English, having the ability to do that, or having the ability to search through a large collection of images. So it's had an effect on a number of things that we do every day. In addition to all that, we at Google are deeply interested in semantic processing. In fact, tomorrow at the lightning talks, you're going to hear some of my colleagues talk about themes that are similar to what the speakers are going to talk about today and tomorrow. So very briefly, we're going to start off by looking at what we mean by semantic processing, looking at some of the difficulties associated with semantic processing of textual data. And then the second talk is going to look at how user-generated content has affected semantic processing and vice versa. And then we're all going to go have some really nice dinner. And then tomorrow morning, we're going to come back, and the first talk is going to sort of focus on how semantic processing can be used in the context of images. And then the second talk is going to be about how we can use semantic processing for searching through a large collection of plots and figures and diagrams and so on. So without further ado, I'd like to introduce the first speaker, Professor Nenkova, who's a faculty member in the Department of Computer and Information Sciences at UPenn. Over to Ani.
Hello. Let's see, I want to find it. Let's start here and see how I move. So one thing that maybe kind of striking difference from the previous session is the big title was additive manufacturing, and then everyone had in their title additive manufacturing and then something else, kind of like what specific sub-area. If you look at our titles, we have semantic processing, and then none of us has semantic processing in our titles. So I just want to take like 30 seconds to kind of explain why this is the case and kind of what do we mean by semantic processing. So really when we kind of, the people who will be talking to you when you say semantic processing, the question that we're saying is, we have a document that's in digital form and we have a machine. What can the machine do to represent the content of this document? And the purpose of the representation is to compare documents, like find similarities, match appropriate documents. So these are the problems that we'll be looking at. And we'll see that the documents will vary in form and some of the representation will be increasingly difficult and complicated. So today I'll be talking about representations for text, and hopefully this would give you some good intuition to kind of actually understand the talks that will come after me. So automatic semantics, what does it mean for a computer to understand a document? And again, in my presentation, I'm focusing on text, but more and more online there are different forms of digital documents, so more and more it becomes important to represent images and then go cross-model and kind of match images with text. So we need automatic semantics because computers help us navigate data. So we want computers to be pretty good at matching what I'm asking for, my query, and the documents they return. This is the most obvious one, and I'll talk kind of in more detail about other kind of finer applications. But even more and more, we actually read more computer-generated text. So we would want kind of computers like doing machine translation, like in the application that Amar was talking about, or automatic summarization, which is kind of area of increasing interest. And we want the computer to be able to understand and kind of match our needs, compare text, or generate a text that has the right semantic properties. And I think this is the last time I use kind of semantic processing. And then I go to like the more usual terminology that we use in our fields. So we want some sort of representation and a way of meaning of documents. And what we want from this representation is for it to let us match documents and compare documents. And there are two aspects when we talk about interpreting text and understanding text. One is, what is this text about? What is the meaning? What is the topic? And this is exactly the type of kind of search-related question that people in our area have studied for, like, I think it's not exaggeration to say 50 years. So some of this I will overview now. But there is also other aspect of understanding that is kind of the frontier of kind of semantic processing and language processing and speech processing, which is, if I see a text, how good is the quality of the text? Is this a text that's easily understood? Is this text clear? Is it informative? Is it well written? And actually, this sort of question is something that researchers have only recently started to look at. And I'll talk a little bit about the applications in this emerging area of research. So a lot of the kind of basic ideas that many of the semantic processing applications are dealing with, say, we employ a vector space model of semantic. What it means is that we'll represent our objects, our documents, as points in space. And the way we will match documents or find similarity between documents is to say points that are nearby each other are similar. So kind of the goal here would be, we have our text, what we want is a vector of numbers, and then we want to compare the numbers. So we'll see this in all of our talks. You'll actually see some clever way of doing this. And for information retrieval, where we have what the user type, the user query, and the documents that are available on the web, kind of a really basic idea is to represent the text as a vector of terms. So each term, each word that appears in the document is one dimension in this vector space. And each vector just represents to what extent the document covers this dimension. So for example, this sentence above, which can be a document, kind of using the term document very loosely, is represented by this. So this is my vector that represents the key in the front pocket of the backpack, is in the front pocket of the backpack. So it has 3 does, 1 key, and 1 backpack, and so on. And this is the representation of the backpack. It's in the car. And kind of what is, like, this is really simple idea. So for a document, what we'll count is the words that appear in it, and these counts would be our representation. And the neat thing is, now that I have a vector of numbers, I can use any sort of distance metric to figure out which are the similar documents, what are the documents that are close to each other. And then basically we'll see that there is kind of, you can build on sophistication, but really the bottom line is this. Like, we turned our text into numbers. Now we are using a metric to compare these numbers. And one similarity metric that kind of works well for text application is the cosine similarity. So once you get the vectors, it's just this component by component similarity that often turns out to work pretty well for comparing texts. So you can say, well, I understand this. This is neat. Like, we just counted, and we got our vector, and we can now compute similarity, so you can find what is more similar to my query, and you can give me this document. But this doesn't seem like a lot of understanding, really. And it turns out the exact same approach can be used for things where one would be surprised, really, a computer can learn this. So similar approach has been used for learning word meaning in this unsupervised fashion. So what we represent here, a word is a vector of context. And the context can be the other words that appear around that word. So imagine we want to know what is red wine and what is green tea. So now, instead of looking at individual documents, you say, I go on the web and I want to see what was occurring around green tea and what was occurring around red wine. So now you accumulate this context, which are words that appear nearby the word that I am interested in, and this is the representation that we get. And suddenly, it turns out, like, by this method that again is kind of count, represent, and compare as vectors, you suddenly start getting really neat results. For example, if you do this method and ask a computer, tell me, according to your counts, what are the words that are more similar to wine? These are the results that you get. So white wine, red wine, beer, Chardonnay, fruit are the words that are similar to wine. And you can say, well, this looks more like understanding. And this is something that can be useful. So for example, one application of this sort of kind of completely unsupervised semantic learning is, imagine I wanted to do a search for additive manufacturing. And this is what I type. But as the speakers were kind of, in the previous session, they were kind of going back and forth between additive manufacturing and 3D printing. So it would be nice for the computer, like when this matching happens, is to know that 3D printing is also a term that I could have typed, but I didn't type. And by having these automatically collected kind of families of similar word, actually the computer, I issue my search, it's additive manufacturing, and the search engine, when it maps document to my query, actually augments the query. So this is the query expansion with these other terms that are very similar, and I might as well have typed them, but I didn't, in order to find a good match. So it's kind of, again, the very same simple idea, but it's already kind of growing in sophistication of what you can do with this. And similarly, you can ask, okay, so can I find synonyms? So if, for example, if I want to analyze people's reviews, how do I know what is positive language and what is negative language? Can a computer ever learn, like, what does it mean for a review to be positive and a review to be negative? And it turns out, with the exact same approach, this work that was recently done at Google, and kind of there have been smaller scale projects before as well, but with the same approach, you can ask, okay, I know that excellent and amazing are terms that can occur in a positive review. Can you do this? Like, just go online, read a lot of reviews, and tell me what are the words that are really similar to excellent and amazing. And this is what the algorithm finds in It's cute, fabulous, top of the line, melts in the mouth. So now, if we want to do sentiment analysis on review, this automatically built dictionary can tell you what are the phrases that you need to look for. And this is really powerful, because what is the alternative? The alternative is that someone sits and thinks of synonyms of how can I talk about kind of good things and bad things, but it can never be as exhaustive as what kind of the actual analysis of reviews has shown. And similarly this, like what are the words that are most similar to bad and horrible? The algorithm finds subpar, crappy, out of touch, sick to my stomach. So unlikely that, and this dictionary is huge. It's thousands of entries. It's completely unsupervised, just based on this model. And then instead of just kind of saying, oh, I want to represent all words, what we want is tell me which are the words that are similar to these kind of polarity words. And now I can do better semantic analysis of reviews and figure out whether people are happy with something or not so happy. And kind of another level of taking this kind of machine learning paradigm is to say, okay, can a machine actually learn that mason and stone is similar to carpenter and wood, because both of them are relations between the two nouns? And it expresses a profession and the material that this profession works with. Most of you actually probably have seen, like, this is kind of the basis of some of the kind of intelligence tests, definitely the basis of language competencies tests that you can get on a GRE or SAT exam. And it turns out that the exact same representation, this vector representation, that is accumulated from vast amounts of text, can be used to train a system to do similarities like this. So here, what you're representing is the pair of words. So this is the item that you want to represent. And the kind of features that you the dimensions are patterns that these words occur in. And where do you find the patterns? A human will not tell you the patterns, but you would go and the system just reads off a lot of text and finds what are the syntactic structures in which these two words appear in. And then by comparing the vectors of these representations, you can say how similar is the semantic relations between these two words. And you can see immediately this is actually building much more understanding, because now we can say in this manner one can build a kind of formal representation that says like scientists can be academic or industry scientists. So this sort of structure, like the type of or works with this sort of encoding, can now be represented in computer form through this sort of analysis. And it's kind of fun, actually. People have tried this algorithm on SAT questions and kind of the multiple questions. So you have an example relationship, and then you're asked of these 5, which one is most similar to the one that I'm showing you. And the performance is above the average of the nationwide SAT scores. So it's not amazing, but it's pretty good. And I think it's amazing just to think about the fact that this sort of actual understanding is based on simple counting. And this is an intuition that kind of is usually very surprising. But it works. So some of the challenges that you'll hear more about, it's kind of, oh, this is too easy. Certainly, it's not just counting. Yes, it is too easy the way I represented it. There are too many documents and too many words. So sometimes these representations are huge. How do you actually kind of fit them in memory? And we'll hear a bit about this tomorrow for the words and picture representation type work. Then reducing noise, I said each pattern that I represent is a dimension, but surely these representations that I was talking about are more than necessary. You have more dimensions than you need. So how do you know which ones to drop and which are just noise and which are kind of throwing off your similarity measure? So this is a research question. Or kind of richer context. Can you use concepts rather than words? Or can you use syntactic relations rather than just a window of words that occurs nearby? For the remaining time, I want to tell you more about this text quality stuff. That is something that I have been working on, which is, can a computer ever actually get an accurate estimate of how well written a text is? And it turns out that some of these kind of frequency-based features that one can derive from large amounts of text are actually applicable for some of these tasks. So what I'll tell you briefly about is 3 case studies that we have done in my lab. One is just asking people, here are some texts, can you give us ratings, and can we figure out what correlated with your ratings? So it's kind of getting started on research. The other one is, can we get a bunch of machine-produced summaries and figure out which are the ones that are written well and which are the ones that are written poorly? And then also, can a machine like see a text and figure out how general or specific is this text? It's a really important application if you think about it. When you're issuing a search in Google, very often you don't want something that's too general, kind of saying like very little information about what you're searching for. So having the right mix is really important. So how well written is a text? We asked a bunch of graduate students at Penn to raise some text, and then this is 30 Wall Street Journal articles. And then we tried various things that we could compute automatically to see what correlates with their ratings. And as I was talking last evening and today a little bit, and I talk about my work in text quality, people ask me, but surely kind of people don't agree. People can have different ratings. So this is definitely true, and we have looked into this. But for this kind of study, in order to get some meaningful results, we just average across 10 judgments. So kind of what we are trying to say is, what are the type of characteristics that would be kind of predictive of the average assessment from people? And one thing that does not correlate with ratings at all are the type of things that if people have ever read or kind of were interested in readability metrics, the type of readability metrics that are used in education and in newspapers to make sure that kind of a text is approachable, kind of understandable for high school level or kind of college educated people, is based on this sort of features. The average character per word, so longer words are supposed to be harder, and average number of words per sentence. These have no correlation at all. And this is actually because we have a biased sample. We have Penn graduate students, so these are very educated people. It's kind of beyond the readability metrics. It's not like saying 8th grade education, high school. It's we're all. Other things is that we found are not at all related are, for example, subordinate clauses. Very often in psychology and education, we would say, oh, kind of simple language, you should use simple language. Subordinate clauses are difficult construction, you should not be using it because people don't like it. It turns out that if you go through graduate school, you're actually pretty comfortable and you tend to like texts that have a lot of subordinate clauses. Same with, it's actually other groups have had the same results. Highly educated people, this rule that you have probably seen in prescriptive writing text, like don't use kind of indirect, he was, the pie was eaten by someone. So it turns out that these constructions, highly educated people, absolutely no problem with. They like them or they don't matter at all. So what did matter for these highly educated people? Number of words, so shorter is better. So this one we did reproduce, and it's kind of nice. The other one that is very related to this kind of collecting probabilities of large amounts of text is that the text probability, where you have collected the probabilities from a large sample, we used words of New York Times news here, 1 year of New York Times news. So the probability of the text under this model turns out to be very predictive. So roughly, does it look like things that you have seen before? And if it does, the ratings tend to be higher. Another thing that turned out to be very interesting is that the average number of verb phrases in the document was very predictive of how well written it will be perceived. And at the time I was surprised, but since then I've been reading a bunch of again, prescriptive writing, and this is exactly what they say. Like, don't use a noun if you can use a verb. And so this would be one thing where we're looking at like finding nominalization, so where you have used the noun phrase. So the growth of the economy did blah, blah. We can find this and say, hey, maybe you should say the economy has grown by that much, and this would be clearer. So it's kind of also pointing in directions where we can actually give automatic feedback on writing through identifying this. So the last one was the really strong predictor of text quality, and these are the discourse relations that appear in the text. So probably many of you have never heard of discourse relations. It's pretty kind of narrowly defined term. So what are the discourse relations? So very often in text you have sentences like these. Mary likes to cook, her husband prefers to eat out. And any human reading this would say there is comparison between the statements. And can a computer actually find out that there is the comparison between these two statements? There's also, he's a reliable person, I would choose him. There is a kind of contingency, like this is the reason why I'm choosing him. Again, it's not overtly in the text, it's something that's implicitly figured out by the speaker, by the reader. And they're temporal relations. So these type of relations are either explicit, so you can kind of, for example, convey comparisons with but and however, and then you explicitly know that you're signaling a comparison. You can have a because or since, and then you know that there is an explicit contingency, but many times there are no overt signals. And it turns out that in order to predict, Amar said I have 5 more minutes. I kind of, in order to get these correlations with how well written is the text, you need both. You can't deal only with the explicit, so you need both in the mix. So this means that if we want to predict this sort of mix, we want the computer to be able to see the sentence and say, there is a kind of reason relationship. There is a comparison relationship that's inferred by reading these two sentences. And this is a really hard semantic processing task. Like, this is something that a lot of people in my field are now looking at, and we also have worked on doing this. And kind of, since I was saying that the kind of mix of these relations is very predictive of text quality, here's for those of you who are curious, what is the mix? So if you look at a text and you see these implicit relations that hold between adjacent sentences and they're not overtly marked, you have about 20% comparison, about 20% contingency, and about 10% temporal. So quite a lot of the text, and about half of all relations are implicit. So about a half of all the relations in the text are of the hard type. And it turns out, so kind of here I won't go much into detail, but it turns out that some of these kind of statistics gathered from a large corpus actually are features that are useful in the representation and kind of being able to figure out, given two sentences, what is the relation that holds between them. For the automatic evaluation of human, linguistic quality of summaries, I actually want to kind of go quickly over this, but here is one thing that we researchers in natural language processing do a lot is, okay, we want to develop automatic summarization systems, and we want to know which one is better. So we have these NIST run evaluations where NIST pays and you submit your system, and the NIST evaluators go and read the summaries and rank them. And a usual kind of participation load is 40, 60 teams. So there are 40, 60 summarizers that are being evaluated on about 50 test inputs. And then people sit and rank, like this is summary that's good in content, but it's really very incoherent, like it doesn't read well. So unlike what I was talking about before, in this setting, we actually have some annotated data. So we have samples of the summaries, and we have what a human NIST annotator have said in terms of their linguistic quality. And one thing that we developed 2 years ago was an algorithm that looks at these summaries and kind of ranks them. And what we want to know is how accurately would we say that one system is better than the other, where the accuracy is determined by what the NIST annotators did. And we were surprised by how good our accuracies were. So we could say which is the better system out of two with 90% accuracy. So fully automatic methods of predicting the linguistic quality kind of only made 10% mistakes on where NIST annotators were working for. Like, it's extremely expensive. I can't give you the exact numbers, but a lot of money is, and the really neat thing with having an automatic method is I actually can use it for development. If I want to have a summarizer that's better, I can actually run this automatic metric and see how good my summaries are. And then for a particular input, the accuracy was a bit worse. So sentence specificity was my next kind of text quality application that I wanted to bring up. And here is an example. And again, this is our predictions from our system that says the second sentence is general, and the first one is specific. And you can see how you actually want to kind of have a mix of both, because if you have a lot of details about what booksellers are saying and what the topics of a kind of sales are, you can say, well, why are you telling me this? And I'm telling you this because I want to tell you that this is a controversial price. So general sentence can set up the topic so that you can bear with me and read the details later in the specific sentences. So having the right mix is really important. And again, we actually trained a classifier that is pretty accurate in predicting on the sentence level, is this sentence specific or general? And it turns out that, for example, evaluative words of this type that I was showing you before, so good and bad, so when you kind of express opinions, these tend to occur in general sentences. So part of speech, like plural nouns, like cats make good pets, general sentences, this is being picked up. And word specificity and also turned out to be a really good feature. And again, like most of these features were kind of collected in a way that was based on this kind of represent and compare vectors type of approach. And the classifier has 94% of agreement when people agree that a sentence is general or specific. And again, we did find that some sentences are just very hard to judge on this kind of binary scale. So when people don't agree, the classifier is not good either. And I will take 2 more minutes to tell you about one analysis that we did that actually opens up a lot of the frontiers of this kind of work where we want a computer to generate text. So we looked at the summarization application, and what we wanted to know is when a system makes a summary, does the system choose specific information to include or general information, and does it matter in terms of the quality of the text that they're producing? So here is the average specificity and the specificity of the inputs. So these are, the inputs are just news articles on a given topic. Like think Google News, like a cluster of articles on a similar topic, and you want to have a summary that says, what was this article about? So this is the average specificity. And then if you ask people to write a summary in their own words, these are the abstracts, the specificity goes slightly down. If you ask people to choose sentences, kind of say, which are the sentences that are most important, like I want to highlight them rather than generating in your own words, the specificity goes way up. And then if you look at these hundreds and thousands of system summaries that were produced in our annual evaluations, they go even more specific. You can say, okay, does this matter? Like, there's obviously a difference. The human summaries are more general, but does it matter? And we looked at it, and it turns out it matters. It matters because, especially for summarization, you can think about the general sentences as ultra-short summaries. So having something like details of Maxwell's death are sketchy, it can summarize a lot of like news writing on the topic, or folksy was an understatement. So we actually looked at these NIST annotators, and it turns out that systems that have more general summaries score better at their content. So people like what the system picked out as good content. But there is a kind of, the flip side was also the systems that included more general information were among the worst on linguistic quality. Why? Because if you say a general statement like this, you certainly want to also give the details of why. You cannot just give it kind of out of context. So for example, if you see this sentence, and instead it's saying like the Bismarck, and this is a sentence that a human actually has included in their summary, it's like, I don't want this, like it has no content, it has no, like it doesn't tell me anything. But if you read it in the context of this previous sentence, which says this person has all the qualifications for the job, everyone thought that he'll succeed, and then you say instead he's saying like the Bismarck, perfect summary, tells you quite a lot. So the problem is, can a computer actually figure out that this is the proper context to include the general information? So this is kind of opening up a lot of kind of interesting new areas in automatic summarization, and we're actually already been able to improve the summarizer by kind of looking at some of these text quality issues that need to be incorporated. So my conclusions, we have seen many successful applications in content understanding, and this is the type of stuff that you'll see in the following presentations. They'll talk more about what are the current applications, more interesting, but there is increasing interest in this more subtle understanding task that draw attention to discourse relations and sentence specificity. So they're opening tasks that kind of people in the field have not looked at before. And it's leading to progress in text quality research, which actually probably we'll all kind of benefit by. So this is what I had. Sorry, my area chairs gave me conflicting instructions on time.
Jamie Heskin, University of Arkansas. Do you see it? It almost looks like you're getting to the point where the computer could write the paper. You know, if you give the data, you give papers in the past and things like that. Do you see that happening in the future, where I can just stick my data in and not have to worry about the paper writing and saying I'm working hard all day?
Realistically, no. I actually, when I did my PhD, I worked a lot on these kind of generative methods for summarizing news, and it was impressive because we have a big School of Journalism, and we would occasionally ask journalists to look at our summaries and help us evaluate them. And at some point they said, no, we won't help you because you'll put us out of our jobs. And we were all like, what are you talking about? We're so far from it. So I don't think any researcher actually kind of realistically would think it would put people out of jobs. But I think it can, the one thing that will make a big difference is this sort of research will actually help us write better. So as you're writing, it will be able to point out some places that you may want to improve, and hopefully we'll be able to generate more and more specific, what is it that you need to improve. And this, I think, is realistic, and this is something that I personally kind of am interested in working on.
So I have a question about how do people react when it makes the wrong recommendation. So, people are very intolerant when it comes to machines telling them that something is incoherent when they actually think it is coherent. So how do people react to comments?
Right. So this is why I have not. So yes, so kind of, I think as systems are getting better, it has to be on demand. So it cannot be something like spell checker or grammar checker that actually tells you it's wrong. Kind of initially, as we were developing, it has to be something where the person can say, tell me if you have something to tell me. So it has to be on demand. We're not at a point where we can say it's a feature, it's on. You have to, as you're saying, for the exact same reason, it would be annoying for many. I would like to use something like this. I mean, I have this problem that, yes, I speak English most of my day, but English is not my first language. So sometimes I want to kind of, and it's more for the beautiful. I didn't get to this, but some of the kind of research is also, is it nicely said? And it's very nice, very easy for me to kind of slip into this very formulaic language. But saying it nicely and kind of more, with more impact is something that I'm interested in, and I actually would want the computer to help me with this, because it's hard for me to do it in English.
Hi, my name is Audrey Ellerby. I'm from Stanford University. So one of the problems that I find today is that there's so much literature out there that when you go to publish a paper, it's almost inevitable that you can't do a thorough literature search, or that you can guarantee that what you're doing is unique and hasn't been done before. Given that so much of the writing that we do is supposed to cover this body of literature that's already out there, do you see this as changing the way papers need to be written so that we don't need to include all of this historical context and we can just focus on the newness of what we've been doing?
It is actually, if you look at our main conference, the Association of Computational Linguistics, in the past 3 years, there has been a growing number of papers that say exactly kind of how to generate related literature search, how to kind of summarize scientific papers so that people can navigate the literature better and kind of more efficiently, kind of making sure that they don't miss anything. Kind of what you're asking is, will the computer be able to generate the related work section or kind of the positioning section for us? Again, I don't think we're right there yet, but I think we're very close to the point where computer will be able to tell you, look at these papers, they're very similar, so it's kind of the first model. And it's also very good, for example, one thing is just, you don't need to just say, X and Y did blah, blah, blah. What you need to say is, and this is how it compares to my method. So you need this either explicit or implicit sort of comparison. And one thing that I think it's feasible to do is to look at a kind of large corpus and kind of help people kind of first see, in your draft, do you have this sort of comparison? If you don't have this sort of comparison, suggest ways in which you can phrase the comparison or access. So I think in terms of writing and assessing, we're pretty close, and there is a lot of interest in this. So I actually do expect some kind of interesting systems coming out in the maybe in the next 5 years, which will impact the way we do research, because it will impact the way we reach literature and probably even write papers. Again, I feel for myself, I would like this sort of tool, and it's very personal. Like some people would say, oh, I know how to write, but I would want to use this sort of tool.
Kathy Vaith, Eastman Kodak. Nice talk, I really enjoyed it. A question I have is that a lot of content nowadays that's generated is not written well deliberately, or it's accepted. And I'm thinking of things like texts or Twitter feeds or things, comments to articles, say the Wall Street Journal articles. For your type of research, can you take what you have and map that to that type of content, or do you really have to treat it as another language that you then have to train on?
I haven't given it much thought. One application that I'm interested in, it's kind of similar to what you're asking, not exactly, but one thing that I have been thinking a lot about is when I teach undergraduate courses, I like to give students articles about kind of the science concepts that are, say, New York Times articles to kind of get them excited. And it turns out it actually is hard to find an exciting article. Even in the New York Times, there's a lot of relevant stuff, but some is like, why did they publish this? It's kind of not well written. So even if, you're saying New York Times is good, but I'm saying even within New York Times, if you're searching, there is average, there's pretty they needed to print the issue, they had to put something type of stuff. And then there's stuff that's like, this is exciting, I want people to read this, and probably they'll be more motivated to listen to me in class. So this is kind of the range of things that I'm looking at for information retrieval, and I really believe that for science education, it's some sort of underutilized resource. Honestly, for my own work, I haven't looked at Twitter and kind of user-generated content as much, but I do know that, for example, at Yahoo, there was work, for example, on user questions and answers. So kind of searching over this, so finding good questions and good answers, and they have some pretty good success with this. So it's not impossible to do, it's just I haven't thought about it.
Nick Feemster from Georgia Tech. Your work on document summarization seems like a synthetic exercise. I'm wondering if there's sort of the converse problem, that it's sort of analytic exercise. What I'm interested in is rather than taking a bunch of documents and sort of shortening it, what I'd like to do is have you trace the provenance or phylogeny, if you will, of a sequence of articles. For example, you see something syndicated or put out on a newswire, and then you see a bunch of people copy it or inject their own opinion or omit or excerpt types of things. And I wonder is there work in that type of thing? Particular motivation might be, for example, detecting propaganda or bias.
There is a lot of it. It's very interesting that you asked this, because just in the beginning of the semester, a PhD student from our political science department approached me with very similar requests, kind of like, can you help me do this sort of work? So what he's interested is he wants to see how the way issues are discussed in Senate kind of influence how the issue will be discussed in the popular media. There is a growing interest, but there isn't like a coherent body of research in this sort of area. There was something a couple of years ago, I haven't seen any follow-up work, but I really liked it. It was more of the sort, okay, I have two concepts of kind of, I think their running examples was the kind of recent crisis and loans. And you can say, hey, I kind of didn't follow the news, so why are these related? So what they try is to chain news articles to show what is the kind of connection between two concepts that a user has asked for. So it was kind of preliminary initial work, but it does exist. So I've read at least one paper in this sort of kind of space of questions.
All right. Thank you, everyone, for questions. And let's thank Ani once again.